All right, well, hello AP Physics students and welcome to your first video lecture. I'm going to try and keep this one short for you. This video lecture will be going through dimensional analysis. Within dimensional analysis, I think there's three main uses. The first would be converting between unit systems, so converting between metric units and US customary. I'm not including that in this video lecture because I'm pretty confident that got hammered pretty hard in your chemistry classes, so I think we should be pretty comfortable with that. And quite honestly, we don't use that a whole heck of a lot in AP Physics. But the two uses that I am going to go through in this video lecture are right here. First is to ensure consistency in expressions and equations, and the second is to essentially derive expressions and equations between physical quantities that we may be working with. What you see down here at the bottom of this slide is a handy-dandy chart that just lists out quantities that we will be using, and these aren't all of them, but they're most of them, all of the quantities that we're going to be using in this course, their units, and then their dimensions, essentially what that thing is. So we have symbols, and the big three symbols are length, time, and mass. As you can see, all of these other quantities, their dimensions are just a combination of these big three, okay? And that's going to be pretty key for us to remember. Now, when we take a look at some of these down here, which are just combinations of these big three, what this is saying is that velocity is always going to be a length divided by a time. Acceleration is always going to be a length divided by time squared. So these dimensions are consistent. They're always the same, and that makes it really easy for us to do the above uses that I'm going to go through in these slides. So our first use in this class for dimensional analysis is going to be consistency in expressions and equations that we use. To me, there's two parts to this. The first is that, and I think it's pretty common sense, we can add or subtract physical quantities only if they have the same dimensions. So, for example, if we have an equation where we have a length quantity and a time quantity, well, we can't add those together, or we can't subtract those because they're two completely different things. Again, that seems pretty self-explanatory. The second one, which I think is the more primary one in this use, is to make sure that we're being consistent on both sides of an equation, that our dimensions actually match up. So at the bottom of the screen here, I have a couple equations, and I just want to go through what this looks like. So the first equation that I have here is Newton's famous second law, and we're going to be delving into that in much detail later on this year. But if we take a look here, force has dimensions of a mass times a length divided by time squared. So what I'm going to do is I'm going to write that down here. So I have mass times a length divided by time squared. Now, on the right side, we have mass times acceleration. So if we take a look, mass, our dimension is m, mass. Okay, and then acceleration, our dimension is L divided by t squared. So you can see that on the left and the right side, our dimensions are consistent. They line up. Now, this is a really simple example. The more prominent way that we can use this tool of dimensional analysis is if we algebraically manipulate an expression or an equation and solve for a particular variable. We want to make sure that that variable we solve for on the one side of our equation then equals all the stuff that we have on the other side of the equation. So I have another equation here, and let's just say that I wanted to solve this for v. So I'm going to rearrange this, just doing a little algebra. V is going to be equal to 2 times our distance divided by t squared. So we want to check and make sure that both sides have the same dimensions to make sure that this is a valid expression. So if we take a look, Our dimension for velocity is length divided by time, so I'm going to plug that in. Length divided by time. Now on the right side, we don't have to worry about the 2. The 2 is dimensionless, okay, but we do want to look at d. So for distance, our dimension is L. And then for time, it's just t. But notice that I have a t squared here, so at the bottom, I'm going to be writing t squared. So looking at this, our left and our right side are not consistent. They're not the same. So that means the expression that we came up with right here, it is not valid. We cannot use that. Now, we did our algebra perfect. We did everything right. I kind of set us up for failure. This is not an actual equation that we would ever use in physics. But for example purposes, because of our dimensional analysis, we know that this expression we cannot use. Okay? So, again, primary reason for using dimensional analysis in this case is to make sure that the algebra that we do is correct, that the expression that we come up with can actually be used. All right, so the last use is deriving expressions and equations. And the best way that I can go through this is to do an example problem. So what we have is we have a simple pendulum, and I'm telling you that the period of a simple pendulum depends on its length and the acceleration due to gravity. So what we're going to try and do is we're going to try and derive a relationship between those 3 variables. So what I have here is I have a general expression written down. So I'm saying period is equal to some constant times the length times the acceleration due to gravity. Our goal is we want to try and figure out what these exponents are, okay? Because that's basically, that is the relation. So the first step to this is we want to write each of these 3 variables dimensionally, okay, in terms of these big 3. So, first, for time, for L, time is 0. For M, time is also 0. But for time, t is 1. Now, for length, L is 1, M is 0, time is 0. And finally, G. G is a little tricky. G is acceleration, so we have an L and we have a t squared in our denominator. So that's actually going to be a t minus 2. So for L, we have 1. There is no mass associated with acceleration. And then time, we have a negative 2. So now what I'm going to do is I'm going to plug each of these expressions back into our original one. So we have for t, L0, M0, T1. That's going to equal K. K is dimensionless. We're not worried about K. And then we have L, which is L1, M0, T0. All right, and then we have to include that exponent. So we have x there. And then finally for G, we have L1, M up to the 0, T up to the neg 2. And then we add in our exponent again. So now what we do from here, we have to go back into our math brains a little bit, and we have to start doing some law of exponent stuff. So what this, I'm going to simplify this down one step, and what we're going to get is we're going to get L0, M0, T1 is equal to K, and this is going to be L1, actually Lx, because we have to multiply the 1 times the x. Still going to be M0, T0. And then for this side, we're going to have Ly, M0 still, and then we're going to have T negative 2y. All right, now simplifying a little bit further. Law of exponents. So we have similar bases here, so we have to add these terms. So our right or our left side is going to stay the same. It's going to be L0, M0, T1. But now on our right side, we're going to end up with just one term here. So I'm going to write L, x plus y, m is still 0, and then t is going to be negative 2y. We're nearing the end. This is a little bit complicated. So now we can compare exponents on either side of our equation. So essentially, these m's just cancel out because they're zeros. But now for L, we have 0 is equal to x plus y. And for t, we have 1 is equal to negative 2y. So now we have two equations, two unknowns. But if we do a little simultaneous equations, what we're going to get here is we are going to get that x is equal to a positive 1/2 and y is equal to a negative 1/2. So what does that mean for us? Well, we just figured out what this x and this y are. So we can rewrite this expression now, and we can say that t is equal to some constant times L to the 1/2 and g to the negative 1/2. We can simplify that even further, and we can say that t is equal to k square root of L over g. So this process will work anytime we're trying to derive an expression and we know the quantities that are going to be represented in that expression. AP is big on coming up with equations or expressions when you're given certain quantities. And oftentimes you can't just pull them right off of the equation sheet. So this is where dimensional analysis becomes very important. We're going to be going through this process a little bit more so we can get comfortable doing it because it is kind of a lengthy process and it's using some stuff that you may not have used for a while. But that is all I have for you AP Physics students. Have a wonderful evening. Take care.